Alright, I know what you're saying. Those are exactly the ones that are into odd parts.
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's pentagonal number theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant. This guy and gang for inviting me.
Okay, so we've got corresponding to partitions. Taken to infinity recovers Euler's pentagonal number theorem. So this is equivalent, and we just take this to infinity anytime we want. This is corresponding to P of n, and this is corresponding to IP of n, the indicators of partitions of n, aka the inverse, with sequence that we all know by now, indicating the generalized pentagonal numbers. Need to correct that. It's not a 2k, it's just a k. Okay, then we have corresponding to our partitions into even parts, k, and gives the partitions, number of partitions on the even k. And it's a indicator sequence, so this will be I of P of E of n corresponding to IPE of n. I don't think we've done that one yet. Well, it's pretty straightforward. We could either multiply these out, or we could take the inverse of this. Let's do that. Let's take the inverse of that. We got 1 over
101, 02, 03, 05, 07, 0.
Let's go one more for 11. And so we would need a -1 factor here. That adds to 0, so we're good. That's 1, so we're going to need a -1 here. 0, 0, dot, dot, dot. This one's actually looking an awful lot more like this indicator, which is zeros and ones, which makes an awful lot of sense because we suspect that this is going to equal, well, look at where we're getting indications. 0, 1, 2, 4,
5, 6, 7, 8, 9.
10, 2.1, 2.2, 2.5. And so we're going to really suspect that at 14, 2.7 will be our next one, and it'll be positive. It's going to be the same thing, doing the same thing that this happens here, same thing happens here. We're inserting a 0 between each entry. That is essentially what's happening there. And then, of course, we have its counterpart, partitions into odd parts. 15, dot, dot, dot. So, what we want then is IPO of n. Okay, so we also have then for partitions into distinct parts. So 15, dot, dot, dot. Indicator sequence IPD of n. We know the sequence is going to be 1, -1, 0. So what else can we do? Recall that in trying to figure out what the heck this one was, we had a run-in with one that counted partitions into parts such that no part was repeated more than twice, and that going down a degree from degree equals 2 to 1 gave us the distinct parts, aka partitions into parts with no repeated part. So we can specify a general partition function in terms of number of repeated parts. And for that, we're going to use a little convention. We'll use a small d for degree as opposed to a capital D for distinct. And actually what we really should say is P, put the D there to indicate what kind of a function it is, but that D is a parameter, so we should probably go N, D. So this function would give us the number of partitions of N with no more than D repeated parts. And the generating function, the Q series for that one, looks like K equals 1 to R.
We more or less did this with the geometric series identity before. Partitions into distinct parts is just a special case of this with D equals 1.
I'll keep my R's. Infinity is implied. Times 1 minus Q to the D1 quantity D plus 1 times K. So this is the Q series for our partitions. So regardless of what the value of D is, the Q series for partitions will always be a common factor over all D. So that's one, that's an identity. Another identity, not as obvious, actually discovered, or folks say rediscovered, and I didn't know it. I thought it was fresh, and I actually even wrote up a little paper, and I was trying to go somewhere with that, and then I did what I should have done from the very beginning, is I went to Sloan's and looked up the sequences, and I found out that it's already discovered. But it's odd because it's just not very much out there in the literature. But basically, partitions into odd parts and partitions into distinct parts we've already seen. But there's another, and that is, I call it, I'm just going to call it suds of N. And a sud is a symmetric unimodal distribution. So these kinds of things are used in statistics a lot, things like that, but the idea behind a unimodal distribution is to say that it's increasing, non-decreasing, up to some maximal mode value, and then it's symmetric, so it's the same thing on this side, the mirror image of it. So that would be a symmetric unimodal distribution. This is always an odd element out. Consecutive numbers don't have to be different. It just has to be. It can't be any less. So you could have a mode value of say 5, and then you could have a 5, 5 here, as many 5s as you want. But there's an odd number of 5s. There's one in the middle that is not reflected in the mirror. It's actually on the mirror's surface, if you will. So the contention is that partitions that may be formed into a symmetric unimodal distribution are equinumerous with partitions into odd parts and into distinct parts. To see this, let's look at 5. Our odd are, we've already done that.
1, 2, 3.
Our distinct.
5, 4, 1, 3, 2, and then that's it. So 1, 2, 3, odd parts. 1, 2, 3, distinct parts.
So where are our unimodal distributions? Well, 5 is 1, and then 1, 3, 1, right? And then 1, 1, 1, 1, 1. All right, I know what you're saying. Those are exactly the ones that are into odd parts. And I just wanted to point out that that does not mean they are the same set necessarily. Let's look at number 7. We had into odd parts.
We had 1, 2, 3, 4, 5. If we go to distinct parts, we've got 1, 2, 3, 4, 5, and none of the rest have distinct parts.
What are our unimodal, our symmetric unimodal distributions? They are 7, 1, 5, 1. And that's not going to work because we need an even number of the repeated parts to be symmetrical. This one here can't work because if we made this symmetrical, we'd have to put 1 in the middle and it would be not non-increasing. Here's one though, because we can do 2, 3, 2, and nope, but here's one, because we can do 1, 1, 3, 1, 1. And this is a no, this is a no, this has an odd number, no, and this is an odd number, so yes. So 1, 1, 1, 1, 1, 1, 1.
Okay, so 1, 2, 3, 4, 5, same as 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5.
And for example, 2, 3, 2 is none of those. It's not. They're not distinct and they're not odd. But it is a symmetric unimodal distribution. So there's actually at least three types or ways of specifying partitions that are equinumerous. For each of these, there's a complement. PO, obviously, we've seen as PE. And when I mean complement, I mean when we take these and these, if we were to take the sequences of these and multiply them together, we would get the sequence for Pn. So if we add them, we're not getting that, something else. But PE and PO, for P distinct and P sud, as far as I've been able to tell, they are the same complement set. And those are SBDs, and that's symmetric bimodal distribution. And that means that there are two mode values that are equal, and then a symmetric distribution on either side. So it's the same thing, only now we're talking about even number. So we're talking about everything is reflected in the mirror, and so you can see it's kind of similar to the evenness of this, but basically the complement to odd is being even, complement to distinct. It's sensible to say, well, that's about as far from distinct as you can get, is that all elements are strictly paired. So I was calling that strictly paired. And so that kind of makes sense, you know, that they are as far from being distinct as they can be, because every last one of them has a partner. So that makes sense as a complement to distinct partitions. And in terms of sud partitions, symmetric unimodal and then symmetric bimodal, again, comes down to an even number of elements versus an odd number of elements. So strictly paired or SBD, that's the complement set of partitions. Let's do 6. Where are our SBDs?
Well, 3, 3. Well, 3, 3 is 1, right? And 2, 2 is not 1. That's a unimodal. But here, 1, 1, 2, 2. We can write that as 1, 2, 2, 1. And then the 6 ones we can write as. So we have 1, 2, 3.
SBDs. So that should correspond to the number of partitions into even parts.
And that would be 6 would be 1, 2, 3, 3.
And that's it. Those are the only partitions into even parts. Some other common partition function definitions include the number of partitions into parts. Okay, misspoke. The number of partitions with largest part j is what I meant to say. Pj, n of j. Meaning that if j is 3, then all partitions that begin with 3 is given by this generating function. And there's an identity that says that this is equinumerous with the number of partitions into exactly j parts. Let's take 7 and say j is 4. Well, there's
1, 2, 3.
that have largest part exactly of 4. So how many partitions are there into exactly 4 parts? Well, there's
1, 2, 3, and that's it. 1, 2, 3, 1, 2, 3.
Let's check that again with 8, and let's say that j equals 5.
So we have 1, 2, 3 that have largest part 5.
And then how many are into 5 parts?
Here's one. Here's another. Nope, nope. And here's another. And then no. So 1, 2, 3. 1, 2, 3.
So, yeah. Okay. This is an interesting way to see this, that identity, and it gives us another identity, actually sort of like a convolution that's applicable to partitions. So, but this is this is just something I had done before. This t to the nk is
the sum of partitions with largest part j summed from 1 up to some k. So a summation of that pj we just saw just a minute ago.
k is 0, 1, 2, 3, 4, 5, except that notice that this is nk, and we're switching around k and n minus k. We're substituting k for n and n minus k for k. It's very confusing, I know, but essentially what we're saying is what is enclosed here are partitions into parts with exactly 3, with largest part 3, plus partitions into parts with largest part 2, plus partitions into parts with largest part 1. This essentially boils down to the sum of the actual partition numbers from k equals 0 up to the floor of n over 2. So we're counting the full partitions, unrestricted partitions, up to k equals 4. And then as we go to k equals 5, then we have n, which is 8, minus 5, which is 3. See here, 8 minus 4 is 4, 8 minus 3 is 5, so we're, largest part 5, not a problem. But here, 8 minus 5 is 3, so largest part 3, largest part 2, largest part 1, those are the only ones we're counting. And so on. We get 6, 8 minus 6 is 2, boom. 8 minus 7 is 1, boom. And this then translates and can be looked at as, here's our 1s, here's our 2s, here's our 3s, here's our 4s and our 5s, 6, blah, blah. So we can see how all of these with the maximum part pre-pended to the sequence then gives us all of the partitions of 8, so that in general partitions of unrestricted partitions are going to be the sum of partitions up to n, floor of n over 2, not a problem. And then after we get past that, floor of n over 2 plus 1, now we are taking only a portion of what's left, all the way up to whatever n will be, so that the very next one, the next pn, because we're going to pn minus 1 here, the next pn is going to be given by all of this. So that, I think, is a helpful way to see what's going on here, and maybe you can see that this where we're counting full unrestricted partitions and then going to restricted partitions, how that sort of translates and is a consequence of our little 2-for-1 plus shipping and handling trick, if you will. So all kinds of things, all kinds of relations, giving us all kinds of identities, equivalences of in terms of counting.
All right, let's leave identities for the moment and focus on the second part of this episode, which is recurrences for partitions and for the sum of sigma divisors function and others it leads to.
I am grateful to the Summer of Math Exposition project and the idea of it that here's a place where we can informally share mathematical teachings and information and research in a less formal environment without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on, and that's it. Thank you very much for watching my video.